We know that in a minimum the function's derivative is equal to 0. So the derivative of this function with respect to x is when it's equal to 0, we have a minimum. So an approach to iteratively find the zero of a function is called the Newton's method. Take, for example, some function f of x, where x is not a vector but just a number, and then we can find its zero as described here in this picture. We start at some starting point, and then we calculate some tangent, then we get next point, and then we calculate tangent, and so on and so forth in this iteration. So xk plus 1 is equal to xk minus f xk divided by the derivative of 4k equals to 0, 1, 2, and so on. Observe that sometimes we need to compute the derivative numerically by evaluation of the function a few times in the neighborhood. So for example, we will compute the delta f divided by delta x for a small delta x, and there are more involved methods for it. So now we want to find the zero not for f of x but for the derivative. So hence we simply replace f of x by f prime x, and we obtain this iteration here. So now we have xk plus 1 is equal to xk minus the first derivative divided by the second derivative. So to obtain a minimum, not a maximum, we need the condition that the second derivative is greater than 0. So let's take a look into an example for finding a zero of a function using what we just seen. So in this example, we will compute the square root of 2 numerically by finding the zero of the function f of x is equal to x squared minus 2. We know that the solution of this function is square root of 2. So now we apply the Newton's method to find the solution numerically. So we take for the first derivative, it's going to be 2 times x, and then we calculate this Newton's iteration from this formula, and then we will get what we want. So in Python we will start with a value of 1, for example. So x is equal to 1 is our starting point, and then we will do this iteration. So this is what we have here, x minus x squared minus 2 divided by 2x. And we see that the true value for the square root of 2 is given here, and only 3 iterations we obtain this value with 6-digit accuracy. Another example is, for example, is to find the minimum of the cosine of x. We know the minimum is of the cosine of x is at x is equal to pi. So this is also a way to numerically determine pi. We have that f of x is the cosine, so the first derivative is minus sine, and the second derivative is minus cosine. So now our Newton update, so x new is equals to x old minus the first derivative divided by the second derivative, and then we'll have that the sine divided by the cosine. And we can also do this in Python. So this time our starting point will be equals to 3, and then we will run this iteration where x new equals to x old minus the sine divided by the cosine, and we see that this iteration indeed converges to pi, and it computes pi is equal to 3.14 with an accuracy of 10 digits after only 2 iterations. So we can see this if we start, our starting point is equals to 3, and then we will do the Newton update, and we have 3.14. So if we start x equals to 1, our starting point, it will converge to 0, which is a maximum of our function. So this is what we had before. So it converges to 0 with some rounding errors, of course. We have here 3 iterations, and we see that it converges to 0, which is a maximum of our function, and which also has the first derivative as 0. So this is a very important point, because this shows that we still need to check the second derivative to see if it is a minimum or a maximum. If we start with x is 100, and then we will get that it converges to 32 times pi, which is a minimum, but perhaps is not the expected minimum. So this shows that the starting point is very important for the Newton's method. It's very important usually for optimization algorithms.